Test, 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 test. Let me know if you can hear me for people online. All right, good morning. Let's get started. Before we start, maybe just a little bit emphasize based on the midterm results, and also based on some of the visits from student to the office. At least some of my impression is that some of you have not practiced assignments enough, right? So the questions in the exam, including the questions that are going to be in the final exam, my style is it will never be any different from the questions that you have done in assignments, okay? If there's any difference, there's a very slight difference. So it basically means the questions should be questions that you have done, you have seen before. So now for this course, assignments are not graded, right? So it's posted self-practice, but you are expected to really self-practice, right? So that's basically my expectation. A lot of people ask, how can I improve the grades? I think my #1 recommendation is, you got to practice assignments. And when you practice that, you have a solution, but don't look at the solution first, right? Do it first. If you can't figure it out, then you can look at the solution, get some hints, and then proceed. Right? So treat each one of the question like an exam question. Give yourself a little pressure, right? So put yourself in the situation. And plus, there's also lecture notes, lecture example, tutorial examples. So and then there's some additional exercise posted on Canvas. So there are enough resource for you to do, but it's a matter, you're going to have to still have to practice, right? It's a math course. So that's how you will prepare the final exam, okay? All right, so this term is a little bit weird. Some people here, some people online, and some people completely disappeared. So I understand there's different reasons, but we still have to learn how to learn. Basically, you have to practice. Okay, so let's start a new topic today. It's called Laplace transform. And the other thing is it probably applies to every course. It always looks like you have more topic covered after the midterm, right? And it's always look more comprehensive, the topics after the midterm. So which makes the final exam sometimes feels a little more difficult, right? Maybe not a little. So that's why you will have probably spending a little more time, right, on the subject. All right, so let's look at the Laplace transform. This is a very new topic. I don't believe we have learned before. So let's look at definition first. Given a causal function, let's call it f of t. So if you recall, causal function basically means the function has a value of 0 when t is less than 0, and the function f of t exists basically only when t is greater than or equal to 0. Then it's the so-called Laplace transform. Is denoted as capital F of S, or we use a operator. Okay, this is how I write it. You can just write a straight capital L. That's fine too. Okay. Or in a symbol like this. So I'll explain this what this means. Okay. It's denoted as capital F of S or L of F of T, and then this capital F of S, okay, is equal to this formula. It's an integration from 0 to infinite. Integrate F of T times e to the power negative st dt. This is the definition of Laplace transform. I'm sure the first impression, nobody will like it. What exactly does this do, right? There's so many things involved here. So let's break it down a little bit here, right? And before we actually see what it gave us, just the superficial meaning of this so-called Laplace transform. So what this basically does is, suppose you have a system, and this system is represented by an operator L. And then you feed the system with a function f of a t, with a signal f of a t. Okay. So we have seen this before. So you can always represent a system with an operator. It doesn't matter what kind of operator it is, but in this case, this operator is the L operator, or the Laplace operator. Now, if you feed the system with a time function with a signal f of t, then the system will spit out a different function called capital F of S. So that's what this L operator does, or the so-called Laplace transform is. Now, if I look at a little bit more, is you look at the input. Okay, the input is in the time domain. So you look at the signal f of t, it's a time function. Okay. And then when you look at the output, and this is not the time domain anymore, this is called S domain. So basically, the operator L is not only transforming. So, sometimes you say, okay, you put a signal into the system, the output of the system becomes from a straight line into a sinusoidal. Right? So that's a transformation, right? But in this case, you put a time signal into the system, and the system spit out a different signal in the different domain called S domain here. And that's because of this S over here. Okay, so if you look at this integral, you're integrating t. So once you finish the integral, then the whole integral here should be left with only a variable s. Right? The t will be gone. So that's why the whole result set here, right, will be a function of s. So this is what basically superficially what Laplace transform does. It transforms a time signal into a S signal. And we'll see what S is. So that's called the keywords, right? What is it called a transform? And we'll see actually the transform fundamentally is a very useful tool. Okay. We actually, before we look at more, we do the transform all the time. Okay. So basically, you in simple words is you change perspective. So let's say, for example, right? You calculate 3 times 2, or just in general, let's say u multiplied by v. Right. So elementary school student said, okay, calculate 3 times 2. That's 3 times 6, right? Yeah. However, once you learned a little bit more, and you learned the log, the line, and what you do know is, if you take ln of both sides. And what does it become? It becomes ln 3 plus ln 2, right? So, and now you look at this, originally, you're calculating multiplication. But once you apply this operation, instead of you're calculating multiplication, now you're calculating what? Addition, right? So this is a transform of perspective. This is also kind of transformation. So you're changing perspective from multiplication to addition. And this Laplace transform is similar to this perspective change. You're looking at the signal f of t in a time domain perspective, okay, originally. And now if you apply the Laplace transform to it, and then you can look at it, okay, from S domain, from a different perspective. So that's the idea. And it turned out that this transformation or this change of perspective can actually reveal so much more information that you cannot even see in the time domain. So that's the idea, right? So for example, right, if you have f of t very irregular, whatever it looks like, okay, this is where you look, this is what it looks like in the time domain. However, if you transform it into the S domain, okay, and most probably sometimes you will see a signal like this, okay? And this is actually the S here, and you can let S later was next we'll see S is actually complex number, so sigma plus j omega. Okay? So omega is a frequency. So the transformation will reveal how much frequency is concentrated at certain location. And that you cannot even tell from the time signal at all, but you can tell immediately after you do this transformation. So that's the benefits of this transformation. So that omega here is called frequency. So we'll see more about this later. Okay? And there's another transformation we're going to learn almost at the end of the term. It's called Fourier transform. We need just to cover that a little bit without too much depth, but you'll see very similar concepts as this Laplace transform. Okay, so now the bigger picture, right? I want you to bear in mind is, so what is Laplace transform? Of course, you can write this formula down, right? You can write down it's 5 times. You will remember that formula. But the bigger picture I want you to remember is you are literally just looking at the same thing from a different perspective. That's as simple as it is. Okay. All right. So now let's go into the detail of the Laplace transform. So first of all, this L operator, this Laplace operator is a linear operator. So if you think of this operator as a system, then this is a linear system, basically. A linear system means superposition rule should be satisfied. And if you have 2 signals and you're trying to apply this Laplace operator, right, to 2 signals like this, then you will get C1 L f of t plus C2 L g of t. That's what a linear operator is supposed to do. Right, so L is an operator transform f of t into capital F of S. Without going into this another branch, and this is a little bit out of the beyond this class here. Now we also can do the so-called inverse Laplace transform. Okay, we can do also inverse Laplace transform. So remember, And I have mentioned that the S added here, the S variable in nature is a complex number, sigma plus j omega t. Then the inverse Laplace transform formula, I'll just write it down here. We probably not going to use that at all. Okay. I'll show you how to find the inverse Laplace transform later. Basically use the table that I handed out today. You put a L to the power of a -1 to indicate that you are operating as this inverse Laplace transform. So obviously you're trying to transform the S function back to the time function f of t. So the results should give us back this time function f of t. And the formula is a little bit complicated, and this is definitely some kind of integrals we've never seen. It's called a complex integral. Okay. So it's 1/2 pi j integrate from sigma minus j infinite to sigma plus j infinite, and then f of s e s t dt at ds. That's inverse Laplace transform. So I'll just write down the formula. We don't need to worry too much about how we actually use it. So we're probably not going to use it at all, right? In your engineering education. But this is a branch called the complex integral calculus. So calculus literally stopping 248, but it doesn't stop in 240 for engineering undergraduate education. But there's more to that, and this is one of the subjects, essentially called the complex integral calculus. Okay. All right. What we're interested, okay, is more of this one direction. Essentially, is this direction. If I apply this formula to a time function, and what kind of a S function would we get? In particular to some very well-known common functions. So this is what we're going to look at next is, let's look at Laplace transform of some typical functions. By typical function, basically what I mean, the functions that I have given out in the handout, right? So the expectation would be you don't need to memorize the results. However, there are some really common ones that you will use that so many times that you may actually want to remember that. Okay. The first page of the handout, as I'm going to show, is the properties of Laplace transform. And the second page is what we're going to demonstrate, and not all of them, because what we're going to demonstrate is how can we transform this column of time function at here into this column of the S function. So not all of them, I'll just show you a few, right, how they are being transformed. Some of the expectation, for example, in the future, okay, if you're doing question, what is the Laplace transform of a unit step function? So expectation should be, it's very straightforward. Okay, 1/s. Okay, so that's something that I would expect you to remember. What's Laplace transform of the impulse function, which is 1, right? So that's something I would expect that you can remember. And this is also a very common one. Okay, what is Laplace transform e to the power of a negative at, which turn into 1/s plus a. So a couple of these are fairly common ones, and sine, cosine, right? So those are, as you're going to see, are my expectations. So let's look at, I'll show you how the results is obtained from the table. So let's first look at the unit, look at that exponential decay or exponential function. Okay, so f of t equal to a times e to the power small at when t is more than 0. So what I'm writing down at here is a causal function. So essentially, f of t does not exist when t is less than 0, and when t is greater and equal to 0, there's some sort of function here. As you can remember, the other way of writing a causal function or write this piecewise function into a single expression is to use the unit step function. So if you multiply this a to the power negative at with u of t, it's the same meaning as writing this piecewise function. So without, if in the future, without emphasizing or without saying further, so all of the functions, okay, like the function listed in this column right here, we're actually referring to a causal function. Essentially, everything in this column here, you can consider every one of the functions like multiplied by u of t. Okay, so we're just now multiplying u of t over here. Is that clear? Yeah. So all of the function we're talking about here are causal function. So let's take a look at Laplace transform of this time function. When you write this operator L, as I said, you could just write a capital L, that's fine, right? Yeah. So we have the formula, so let's apply the formula. So 0 to infinite, current function is a to the power negative EAT, and then multiply by e to the power of negative ST dt. I mean, technically, you can certainly, if you want to be a little more accurate, so you could certainly write this u of t out of here. However, it doesn't really change anything because u of t means u of t equal to 1 when t is more than 0, right? So the integral is from 0 to infinite. So that multiplication of u of t out of here, it doesn't really do anything at all. So this essentially you can erase it, right? Because it's just 1, right? So that's why we don't need to worry too much about that. So this is the formula for the Laplace transform of this particular function. So now let's calculate this integral. You have a multiplication of two exponential function. So e to the power of a plus e to the power of a multiplied by e to the power of b equal to e to the power of a plus b. So you get e to the power of negative s plus a times t dt. So that's the simple simplification. And then you calculate the rest of the integrals just like an integration, right? So you know that when you integrate e to the power of, for example, a t dt, the result is e to the power of t. Well, the only difference right now is you have a coefficient over here, negative s plus a. So the integral of this one is not too bad. So it's a over s plus a, then e to the power of s plus at with the limit 0 to infinite. Okay, so the t, right? This is the limit for t. So t goes from 0 to infinite. I'm going to substitute the 0 to infinite into the exponential there. Okay. I'm going to leave this infinite for now. Okay, so leave the infinite. So just consider it's a very large number. So let's plug t with infinite. And then t, plug it as 0. Okay, so this one is easy. So anything times 0 is 0, and then e to the power of 0 is 1. So this term here is basically just a 1. All right, but this term, So this term needs a little bit of examination. So e to the power something, negative something, multiplied by an infinite. So if you think about it, it could be 0 or it could be infinite, right? It really depends on what? Depends on the value of s plus a. Okay. So we need to look at this, okay, separately. So let's look at this term. Now I'm going to go back to the s variable. Okay. So if you recall that the s by nature is a complex number. Okay. So when Laplace created this or developed this Laplace transform, okay, this is basically what happens. Sigma is, s is a complex number. Okay. So sigma plus g omega. And this is what we're going to do. We're going to replace the s with sigma plus g omega and plus a, and then times a very large number infinite. So you got a real number sigma and a. You also got the imaginary part g omega. So I can separate this into the two parts. One is negative sigma plus a times infinite. The other one is negative j omega times an infinite number, okay, or a large number, whatever you call it. Okay, right, so that's what this one is transformed into this. All right, so now let's first look at this term. So e to the power of j omega times a very big number. So if you recall, when we learned complex number, and we have the theory called what? Euler's formula. So when you have a e to the power j omega, what it does is you have basically cosine negative omega times large number plus j times sine negative a and times a very large number. Okay. Yeah. So cosine sine, the nature of cosine sine is what? It doesn't matter what this infinite is, right? You plug in a number, you plug in an infinite number. The nature of cosine sine is always what? Oscillate. Okay. It's always oscillate. So it doesn't converge. These numbers here, they always oscillate between -1 and 1. So now let's look at this term at here. So the idea is there any way we can actually make it converge to 0? So then this term actually can be gone, right? So obviously, if this sigma plus a is more than 0, so if this is more than 0, then this exponential term, as the infinite number or very large numbers plug it over there, it will be what? It will go to 0, right? That's called an exponential decay function. And that condition only applies if the sigma plus a is a positive number. And of course, if this is not positive, then that term will not converge to 0. And if this term converges to 0, then it doesn't really matter what sigma, this infinite is. The second term is just some sort of value, then times a 0, then you end up with a 0, right, together. So this whole term over here will be a 0 if sigma plus a is more than 0. And that's equivalent to say sigma is more than -a. Or what's a sigma? Sigma is the real part of this s variable. So it's the real part of the s variable more than this -a. So in other words, I could say if the real part of the s more than -a, then if you look at the results of the integral, so this term is 0, this term is 1, so -1, multiplied by the negative gone. So the whole transformation end up with just a over s plus a, right? So then I can conclude that the Laplace transform of A times e to the power of a negative AT equal to 1 over A over S plus A. But don't forget that's if the real part of S is more than this negative A over here. So this condition, right? So this condition in here is called region of convergence. Okay. So you have a region of convergence to give you the results A over S plus A. Now, I'm sure you might actually start dreading of this. Do I need to do this every time? The answer is no. Okay. You actually don't have to worry about the region of convergence, right? You look at if you look at my table over here, there's nowhere mentioning the region of convergence. So the reason I'm doing for this question is to demonstrate the result, how the result is obtained. And in the back of these results, there is a concept called region of convergence. But when we apply the table of the results, Laplace transform, as an engineer, so we typically don't worry too much about the region of convergence mathematically. But mathematicians, right, you need to be vigilant. Okay, so what is the region convergence, right, for that Laplace transform? For us, okay, that's fine. So basically, behind each one of the Laplace transform, okay, each pair of the Laplace transform, there is a region of convergence. However, right, so that's out of the scope of this class. You don't have to worry about that. But this is a legitimate result, okay? The results of this conversion, right? Like this one here, you plug A here, then you plug A over here, right? That's basically what this table is giving us. All right, that's the first example of Laplace transform. Now let's look at another one. Is that the unit step function? So unit step function is supposed to give us, as you can see, this 1 over S right here, right? So let's take a look at if this will give us this 1 over S. So we're doing Laplace transform for unit step function U of t. You apply this formula for Laplace transform. So formula is 0 to infinite f of t e to the power negative st dt. Just write a few times, it will be yours. Okay, so then f of t right now is u of t. You can put u of t here, then multiply by e to the power negative st dt. The u of t is 1, right? So when t is more than 0, u of t is 1. So that term really doesn't play any effect at all. Okay. So you end up with just this integral. And this integral will give you 1 over s e to the power negative st. Then you plug in the limits 0 to infinite for the t. Okay. So technically, right, I should go through exactly the same procedure as we did in example number 1 to find the region of convergence, and then you get the results. Okay. However, we're going to assume there's a region of convergence. When you plug infinite there, you will end up with just 0. So the whole thing will give you just 1 over s. So there are many other examples in the lecture notes. I don't think we're going to go through every one of them, okay, to demonstrate every one of the proof. I'll just selectively cover a couple of maybe three of them. Okay. Any questions so far? Okay, so let's look at Laplace transform of another function. Let's look at this one. What is the Laplace transform of sine omega t? Sinusoidal function with a frequency of omega. So we're looking for Laplace transform sine omega t. Now, for this question, okay, now instead of applying the formula, which is this formula, okay, we'll use a slightly different approach. And we'll use an approach essentially based on some of the results that we have derived from example number 1. So here is one fact that I want to jog your mind. E to the power of j omega t, according to Euler's formula, is cosine omega t plus j sine omega t. Okay, yeah. All right, so then I'm going to take Laplace transform of e to the power of j omega t. So let's take the Laplace transform e to the power of j omega t. And with this term, even though this is a complex function j omega t, but technically, right, the format of this function is no different from what we just did, like this. So, Laplace transform e to the power of a negative at. Because this is also exponential function, and this is also exponential function at here. And we just did this one, which give us s plus a. So if I apply the same results from here, so let's see what we can do, right? This is negative a and becomes s plus a. So currently, then for this one here, what is a? Whatever the coefficient in front of t is the negative a, right? So this g omega here is the counterpart of this negative a in this function. So then if you have a negative a turn into s plus a, then the g omega. So can you actually tell me something? So what should that be? S plus or minus what over here? Exactly, right? Okay. So the e to the power j omega t's Laplace transform basically become 1 over s minus j omega. Okay. Now, I don't want to keep a j omega at it here for sure. So I'm going to simplify this expression a little bit. We call it simplification, but may not be. Anyway, so I'm going to multiply s plus j omega to both of the numerator and the denominator. We multiply both to numerator and denominator. We'll keep the numerator as it is. And the denominator, you have s minus j omega, s plus j omega. So that gives you s squared and minus j omega squared. Okay, and then j omega squared, right? G is square root of -1. So square root of -1 to the power 2 is -1. So then this bottom here becomes s squared plus omega squared. Okay, so that's a little bit simplification. And then I'm going to separate this term, okay, into two terms. One is s over s squared plus omega squared, and then j omega over s squared plus omega squared. separating into two terms. So the real part and the imaginary part. So basically, the Laplace transform of the e to the power of j omega. Right? So we're looking at, this is the Laplace transform e to the power j omega t. It is given by these two terms. And go back to your e to the power j omega t. This is your e to the power j omega, which is cosine omega t plus j sine omega t. So technically, remember, Laplace operator is a linear operator. So the Laplace transform of e to the power j omega t is equivalent to this expression. So you essentially, you're calculating Laplace transform of individual terms. So now I can do a comparison. I have the result of Laplace transform e to the power j omega t, and that's equivalent to this one at here. So you can do a term by term comparison. You see this basically the result corresponding to this term, and that is the result corresponding to this term. Right? Got a j here, j here. So now I get, without using the formula, right? Without using the formula of the actual Laplace transform formula, so we get the Laplace transform of sine omega t is omega over s squared plus omega squared. And then cosine omega t is s over s squared plus omega squared. If you look at the table, and that's the same results that we have just derived. Okay. So again, there are so many, not so many, I mean, there are different other time functions listed in this table here. Without demonstrating all of them, if you're interested, you can certainly derive yourself using some of the form in practice, but you're not required. Right? And some of this actually can be derived based on some of the properties that I'm going to show you next. You know, for example, if you multiply a cosine omega t or sine omega t with an exponential term, then what is the corresponding Laplace? So that's something that I'm going to show you next. Okay, so far, these are the Laplace transform of typical functions, right? So next, I'm going to show you a few properties or more examples. Some of the more examples and properties, basically, I'm showing full screen here. Anyway, okay, so first let's look at another. I would call it, this is more of a property. Right? So what is the Laplace transform of e to the power negative at times f of t? So you got a function, time function f of t here, and then it's being multiplied by an exponential function e to the power negative at. The result of this is what we call S shifting property. Okay, so let me show you the results. Very quick proof like this. Okay. Because this is your function within the operator of a Laplace transform. So according to the original formula of a Laplace transform, you are transforming this whole function. So this is the original formula. So considering this is your original, this is the current function. And then you got two exponential term. So you can group this together, which becomes negative s plus a t dt. So if you compare the expression with the original Laplace transform for f of t, right? This is your original formal Laplace transform for f of t. The only difference is this is s plus a instead of s over there. Okay. So technically, right? Technically, this is, again, this is a kind of a transformation. So as a matter of fact, this is more a generic transformation. So you can literally replace the s with something else, with a k, with a u, whatever you want to call it. In this case, it's s plus a. So your transformation out of here basically is f s plus a. So the s is changed to s plus a. So as you can see here, your f of s, right, is the Laplace transform of f of t. So next time, if you see any function, time function multiplied by an exponential e to the power negative at, then you don't need to recalculate, right? Then you just have to shift this s by s plus a, shift to the left by a, then you got the Laplace transform for this one. So that's how, if you look at the table, if you multiply cosine omega t with e to the power negative at, and cosine omega t we just derived, which is this one here, s over s squared plus omega squared. Now, according to the property we have just derived, all I need to do is replace the s with s plus a. And then we get the Laplace transform of this function. Okay. Yeah. So this is the idea of using this so-called S shifting property. All right, so let's look at the one more example. I think it would, let's probably look at this example as worthwhile. Let's look at the Laplace transform of the impulse function delta t. Now, instead of using Laplace transform delta t, I'm going to do a little more generic. So what is the Laplace transform of delta shifted impulse function t minus a? And consider a is more than 0, it's positive. So basically, your impulse function is over here at the t equal to a. Okay, so I'm going to apply the formula for Laplace transform. This is the formula of Laplace transform. So delta t minus a. And if you remember, whenever you multiply a time function with a delta function or shifted delta function, because delta function exists only at t equal to a, so you can simplify the e to just simply s times a. Because other than t equal to a, and the delta function does not exist or 0. So now, because you're integrating with back to t, so this is basically considered as a constant, so then you can take it out of the integral. And can anybody tell me what this integral is? So you're integrating from 0 to infinite. Infinite is over here. This is your integral limit. You're integrating this delta function. So this delta function, if you recall that, what should be this integral? 1, exactly, right? The area underneath this impulse function is 1. And this integral limit include that delta function. That's why it's 1. So you end up just leave negative s e to the power negative sa. And that's your Laplace transform for delta t minus a, right? Shifted. But if you wanted to know what is Laplace transform of delta t, so all you need to do is you let a equal to 0. So at a equal to 0, then you get e to the power 0 is 0 is 1, right? So Laplace transform of this equal to 1. Okay. So I think I'm going to stop here, and we're going to cover a few more properties of Laplace transform. And most importantly, what we're going to look at is the applications of Laplace transform in solving second-order differential equation. Okay. All right. So feel free to come by if you got any questions.